Hey, what's up, guys? Yeah, so very quick lecture is to prove the following. So, since I know that I have heard about optimization problem, right? So, there is a theorem says that the non-convex optimization is NP hard. Okay, so there is a simple theorem that I think I proved previous. So I will post the link below. Is that you can check that if your function is convex, let's say your function is from real to real. If your function is convex, then you can prove that the local minimum will be the global minimum. Okay, so this is very and the local minimum can be solved by many methods. But this theorem tell you that the non-convex function optimization is NP hard, so which is really hard. Okay, so this is what I gonna to prove in this video. So let me just formulate the problem. Okay, so formulate problem is that, let's say somebody give you a function which is multivariable. Maybe, oh, by the way, this can be multivariable. Let's say x1, x2 up to xn. Okay, so the task. So since it's NP hard, right? So we need to change it into a decision problem. Okay, so task is that somebody give you a function f. Hopefully it's continuous. Okay, and then you're given c. Okay, so c is a real number, and then your question is ask whether there's a input, let's say x1 bar, x2 bar, up to xn bar, such that f x1 bar, f x2 bar, xn bar greater than c. Sorry, less than c. Okay, so this is our problem. We need to find a minimum. All right. So if you can tell me this, then you can solve this optimization, right? Because optimization means that I want to find a minimum. So if you choose the c to be minimum, then answer will be false. If c is not a minimum, the answer will be true. Okay, so this is the decision problem of the general function optimization. Okay, so my claim is that the task, this task is NP complete, or sorry, it's NP hard. So if I want to prove this, then I want to show that you can do a reduction. So I want to show that you can do a reduction to something which is you can suppose that you want to prove that if you assume that you can solve this task easily, then basically you can solve another NP complete problem. Okay, so the target will be the subset sum. Okay, so the simple recap for subset sum is that let's say we have, let's say, A1, A2, AN is a subset. Sorry, is a set, and then we want to find some subset S belongs to, let's say, one. Let's say this set is A. Let's call A. So we want to say that we want to find a subset S in A, such that if you do the summation or the element, let's say called X in S, do the summation of this will give you 0. Okay. So, and the simple proof is that this guy is NP complete. So this guy is already proved to be NP complete. So I want to show that if I can solve this optimization problem, then I can solve this subset sum. Okay, so let's go to the proof. Okay, so let me just assume that let's say somebody give you a set, let's call it A and A1, A2 up to AN, and your goal is to find the target sum. The subset sum. So you want to find S, which is a subset of 1 to 2 to n, such that the summation of I belongs to S will be 0. Okay, and if you want to prove that you can solve this by solving this using the using the optimization. So proof is this, right? So you can consider as f is x1, x2 up to xn. Okay, and then you make an assumption that you add a constraint that all xi greater than 0. Okay, and then you define this to be summation of ai xi from 1 to n square plus summation of I xi 1 minus xi. Okay, so suppose you can solve this. If somebody give you oracle that you can solve this f, find the global minimum. So suppose you can find the global minimum, that you immediately get the following, right? You get ai xi I from 1 to n is 0. And you also get that either x1 is 0 or 1. Okay, because this guy need to be 0. So either xi is 0 or 1. But this xi equals to 0 or 1 is the same as that whether you can choose a subset sum such that summation ai is 0, right? Because I can take s to be I such that xi is 1. Then this will this s choose will make this equation become summation of ai I in s is 0. Okay, so which proof that the target sum, the non-convex or general function optimization is NP hard by doing the reduction to the subsystem. See you guys next videos.